On a problem of extreme and urgent interest, a new state of matter, which has appeared recently and which we have been struggling to understand. It's Kofifi, so it's not clear what kind of a topological entanglement entropy, non-abelian anyonic field theory you need to understand Kofifi, but we can tell you it's a really mysterious and challenging problem. And unfortunately, we haven't made any progress on Kofifi, so I have to report on something else as a fill-in. So what I want to talk about is orbital selective Mott physics, and the context is high-temperature superconductivity. And this is a PhD work of these two guys, Peter Sproul and Andrei Kostin, who work here at Cornell. Okay, so put up your hands and ask questions, please. Okay, I'll play the role of Sean Spicer, and you can play the role of the journalists in the audience. So I will attempt to be more coherent than Sean Spicer. Okay, so we're interested in high temperature. We're interested in room temperature superconductivity, and you know how to get there. We have three examples of how to get there now. We have copper-based high-temperature superconductivity. It's about minus 110 degrees centigrade. Iron-based, maximum now is somewhere near minus 160 degrees. And hydrogen-based, maximum is minus 70 degrees. So the hydrogen-based material is at some enormously high pressure, but it actually is a room temperature superconductor. This room temperature, external temperature goes below this in Greenland and also in Antarctica. So this is a room temperature superconductor. What it shows is just as a matter of principle, you can make a room temperature superconductor. It's not some mysterious challenge that cannot be solved. Easily, someone in this room can solve this problem. Whoever solves it and gets the patent will become a billionaire, because room temperature superconductivity would revolutionize information technology, energy generation and transport, medicine, just uncountable things. We would replace everything where we use gold and copper for conductivity with a completely dissipationless room temperature superconductor. So it's on the way. I believe we will have a room temperature superconductor before we have a laptop quantum computer. So okay, so here are the two, now for the ugly reality. So we have two compounds with which we can work to try and understand what's going on. So one of them is copper oxide, a square lattice of copper, oxygen, copper, oxygen. And the crystal symmetry is a tetrahedron of oxygen atoms surrounding the copper. And that lifts the degeneracy of the d orbitals in the copper atom such that the dx squared minus y squared orbital is on the top of the manifold. And it's in a 3d9 state. 2 electrons have been removed by the oxygens, so that the other orbitals in the iron manifold, the T2G manifold, are all completely full. So there's one half-filled dx squared minus y squared orbital on the copper side. Now, iron superconductors, we have iron and selenium, or iron and a chalcogenide, okay, in a slightly different symmetry lattice. And three-dimensionally, the actual crystal fields from the chalcogenides or the pnictides are cubic. So they also lift the degeneracy of the d orbital on the iron atom, but they do it in the opposite direction. So the top of the manifold now is dxy, and below it is dxz and dyz, and right down at the bottom is dx squared minus y squared. It's like you take the copper manifold and turn it upside down. And furthermore, because of the Hund's coupling between the electrons in the iron atoms, you have one electron in many of these orbitals, and these electrons are correlated magnetically with each other. So somehow this object and this object conspire to make very high temperature superconductivity, and one would like to understand why and how. So here's the so-called phase diagram of these two compounds. So you can alter the average occupation of this orbital on the copper side by removing some electrons or hole doping. You get the highest temperature ambient pressure superconductor known. Tc max is about 165 Kelvin. Or you can add electrons, which means you're actually adding them to the upper dx squared minus y squared orbital. These are split by Coulomb interaction. And then you get a high TC superconductor, but whose TC is a little lower. The parent state that exists here, which you're doping, is actually a Mott insulator, and I'll come to that in a second. In the iron compounds, you know, you're adding or taking away electrons from some of these orbitals, depending on how correlated they are. When you remove electrons, you get a high TC superconductor. When you add electrons, you get a high TC superconductor. In both cases, magnetism, antiferromagnetism in these compounds is diminished by carrier doping. Over here, antiferromagnetism is diminished by carrier doping. And on this side, a mysterious fluid, electronic fluid called a pseudogap appears. So let's just think about the copper case. We have a reasonable understanding of the copper case. Okay, it's a Mott insulator. The on-site Coulomb interaction of this electron prevents double occupancy, and so all of these electrons are localized. Second-order superexchange produces a strong magnetic interaction between adjacent spin-half electrons. When you carrier dope this, especially with holes, it does two things. It suppresses the antiferromagnetism, and it allows metallic transport and superconductivity. So where could the superconductivity come from? So Phil Anderson's proposal is that it comes from here. This magnetic interaction, even if you destroy the long-range magnetic order, the strength of the superexchange remains. If you want to minimize the total entropy of the system or free energy of the system, you could pair these guys into singlets and make a soup of singlets, which would be, according to the Anderson view, a high-temperature superconductor. So that would be lovely. If that was a universal solution, we should search for other Mott insulators which have high J, dope them, and then they should turn into high-temperature superconductors. However, the other compound we have available is iron. So the iron compounds are metals. They're so-called bad metals. They're reasonably poorly conducting metals, but they're certainly not Mott insulators here. You can drive charge through them relatively easily, and we know what the band structure is. So what carrier doping does is actually it moves the chemical potential through this band structure, at least if you take a free particle point of view. So that appears quite different, dramatically different than this argument. So okay, now I speak for myself. This is very annoying. You would like to have a universal mechanism with which you could attack this fundamental problem. If every example of a high-temperature superconductor is going to have its own mechanism, then it's more or less biology. It's not physics, right? So I would, so for me, I'm motivated to try and find out what's universal, what's common between these very different electronic structures and these somehow similar, but in terms of the parent state, very different phase diagrams. Okay, any questions? All right, quasi-particles. So the electrons are viewed as being describable as momentum space eigenstates whose momentum is related to their wave vector. We work in real space. It's also related to the wavelength, which is the thing that we can see. So in an interacting system, you could describe this object by a propagator, a Green's function, and the pole of that Green's function, where the denominator sums to 0, would tell you where there is a well-defined eigenstate, if such a pole exists. Now you can, for weak enough interactions, you can approximate this accurate equation by something like this. And then if you do so, you can solve in this approximation where the imaginary term is much less than the real term, and get an approximation for this Green's function. When you do that, you end up with a number above the 9, a numerator, which is less than 1. That's called a quasi-particle weight. I'm going to talk about that a good deal in the rest of the talk. You can think of it as the amplitude of this wave function if you want to think in Schrödinger-like wave functions. Or if you're a self-energy person, you can think of it in terms of the derivative of the real part of the self-energy. Or if you're an effective mass person, the effective mass is related to this parameter. Okay. So we have machines that can visualize quasi-particles. That's why I'm here. Okay, they're spectroscopic imaging STMs. We've been using this one for what I want to tell you about. And here's what we can do. Look in real space. There are impurities. If there are coherent quasiparticles at every impurity, they're scattering interference. An incoming quasiparticle scatters from the impurity, reverses momentum, and then interferes. The incoming and outgoing quasiparticle interfere. The interference pattern at each impurity has a q vector, that's a real 2 pi over its wavelength in real space, which is related to twice the k vector of the eigenstates, because you had to go from k to minus k to produce the interference pattern. So you could take the Fourier transform of an image of the density of electronic states. It would tell you the q vector of all these incoherent scattering interference patterns. That q vector is related to the k vector by this simple equation in a parabolic two-dimensional band. So now by using energy resolved STM, let's see if this works. Yeah, by using energy resolved STM, you can image this thing, the Friedel oscillations as a function of energy, take the Fourier transform as a function of energy, and extract the momentum space electronic structure. That's the utility, the power of this technique. From real space information, you can get back the momentum space information. So that's cool. Now let's talk about orbital selective physics. So first of all, here's the Mott phase of the cuprates. Okay, I'm not going to say anything about its orbital selectivity. If you just focus on the copper atoms, it's very simple. The dx squared minus y squared lower Hubbard band is down here. The upper Hubbard band is up here, and they're split by a large voltage. It's believed but not known for certain to be somewhere 7 or 8 volts. It's a very large voltage. And because the oxygen band is in between, the actual magnitude of the gap in the density of states, this is the charge transfer gap, is about 3 volts in the cuprates. This is very well known. The super exchange between these copper spin halves produces the antiferromagnetism. Super. So that's the Mott insulator state of CuO2. Now let's consider orbital selective Mott phases. This is a relatively new idea. It's emerging from DMFT calculations. So let me just give you a cartoon of what this idea is. So here's a band. So this is, let's say, density of states, and this is energy, and this band is filled to here. But now suppose there are 2 active orbitals instead of 1. So here we just have 1 orbital, which is split. But now imagine we have 2 orbitals on this side. So if there are 2 orbitals, it's formally possible, and it's found in these calculations, that you can end up in a situation where 1 orbital undergoes Mott transition and is split by on-site interactions, while the other orbital is not, leaving it in a metallic state. That's an orbital selective Mott phase, as defined in all these papers. Now, one thing that motivates this very strongly is Hund's coupling. Because if you have an atom with Hund's coupling between 2 orbitals, what the Hund's coupling do is it aligns the spins in the 2 orbitals, but it suppresses the charge fluctuations between them. These are 2 orbitals on the same atom which stop communicating because of the Hund's coupling. Once the charge fluctuations are suppressed, then each orbital can have a different fate in forming the band structure. One of them could become localized, and the other one could become delocalized. That's why this diagram here of orbital selective Mott phases depends on the strength of the Hubbard term on site, but it also depends on the strength of the Hund's coupling between the orbitals. Yes?
Hund's coupling?
Pardon?
What is Hund's coupling?
So Hund's coupling, you can minimize the free energy of a free, typically d electron atom by having this, like iron, by having the spins in the different orbitals all be aligned in the same direction to make a high spin state. Now, when this happens, DMFT calculations show that as a function of doping, you can alter the degree of orbital selectivity. So this is for an iron-based superconductor, and this is the quasiparticle weight. So for some orbitals, and now I'm colorblind, so I can't read this thing, but for some orbitals, the quasiparticle rate collapses very quickly as a function of doping, and for other orbitals, it remains robust as a function of doping. There's a simple way of imagining that. Suppose you have 2 orbitals, and they're split from each other, and they could undergo orbital selective Mottness. Now, as you alter the chemical potential, you bring it closer to the upper orbital. That means you push the upper orbital closer to half filling. If there are strong interactions, then the upper orbital can become a Mott insulator, leaving the lower orbital in a metallic state. And when it does so, the quasi-particle weight should change dramatically, and also it should be different for different orbitals. So this is a strange situation. Imagine a Fermi surface. You label each momentum state on the Fermi surface according to where its predominant spectral weight was in orbital space. But then some regions on the Fermi surface dominated by one orbital might have robust quasi-particle weight, and other regions might have a very tiny quasi-particle weight. If that happens, so suppose orbital selective Mott phases exist in nature, an immediate implication, which was realized only a couple of years ago, so let's say starting in 2011, is that you would get orbital selective superconductivity, because some orbitals would be coherent and have large enough spectral weight to form Cooper pairs. I mean, some quasiparticles with an orbital identity would be coherent enough and have large enough spectral weight, and others would not. So the prediction is that you should find orbital selective superconductivity if you have orbital selective Mott phases. Okay, so where to look? This is one of Gaby Kotliar's maps of the correlation strength in the iron compounds. And over here, for example, in the iron arsenides, iron selenides, you actually start to get very strong electron correlations. So a place to look for orbital selectivity would be over here, orbital selective superconductivity and orbital selective Mott phases. I showed this to Gaby a couple of weeks ago, and those of you who know him know what he would say. He said, well, I already know that orbital selective Mott phases exist, so I don't need experiments. Anyway, so we know that in this iron selenide compound, there are strong orbital selective correlations. That has been detected by photo emission. The bands near the chemical potential are much too flat. We made a band structure model working with Brian Anderson and Peter Hirschfeld for iron selenide, and it's our best match of photo emission, quantum oscillations, and our own data. We tried to parameterize the band structure. I'd be glad to explain this to anyone who wants to know, but putting aside all these details, it tells us the following thing. Here's the Fermi surface. Here's the first Brillouin zone. This pocket near the center of the Fermi surface is dominated by two orbitals, dxz and dyz. This pocket is dominated by dyz and dxy, and this pocket is dominated by dxy orbitals in this model. So we could segregate the Fermi surface into where the spectral weight is coming from different orbitals. We're using that piece of information to motivate what we're doing. Okay, so now how do we visualize this situation? This is the surface of bismuth selenide. So when you look down on top, you see the selenium atoms. Every dot here is a selenium atom. So that means the iron atoms are diagonal. This is the A iron axis in this domain, and the A iron axis in this domain is pointing in that direction. This is a twin boundary. So now we image the quasiparticles in this iron selenide compound. Now what should we expect? If you just look at this pocket here, imagine that it has an isotropic energy gap on it. Suppose the energy gap is very large here and very small there, just for the sake of argument. And now you go to a range of quasiparticle energy below the maximum gap. Well, you're below the gap here, so you don't see any quasiparticles. But you're above the gap over here, so you do see quasiparticles. That means these regions of momentum space have a very high density of states. You can show that mathematically. The joint density of states from scattering dominates the interference. So if you put an impurity into a compound in this situation, and you measure the scattering interference at this particular energy, you'll see three predominant scattering vectors here, there, and there. And similarly, I could make the same argument for this band. If it has a highly anisotropic gap, it would have three predominant scattering vectors. Furthermore, if you had a model for the gap as a function of momentum, then you could predict what happens to these scattering vectors as a function of energy. That's a natural property. Yes?
I can't see through if there are degenerate states in your iron selenide.
Yeah.
I mean, as you fiddle the D and the orbital stuff, are there equally good degenerate?
Good question. So it should be from DMFT that dxy would be split, fairly strongly split, from dxz and dyz, which otherwise would be degenerate from symmetry considerations. And then the other two orbitals, the x squared minus y squared and dz squared, would be far below the chemical potential. So we're thinking of 3 active orbitals, 2 of them being degenerate. However, this compound is orthorhombic, and the orthorhombicity lifts the degeneracy between dzx and dzy. So all 3 primary orbitals should be split from each other in energy. Okay, so now we carried out these experiments. We can visualize. This is an image of scattering interference of the quasi-particles. This is its Fourier transform. This is a model for what should happen on the band in the center of the zone. And indeed, we see the 3 Q vectors we're looking for, and they're moving to the locations that we expect. And then similarly, we can do the same thing for the other band near the pi0 point in the zone, and also follow those 3 Q vectors. So this is an arcane procedure, but what it allows us to do is to determine by measuring these Q vectors as a function of energy for 2 different bands, and then solving the geometrical equations telling us where the scattering interference was coming from in terms of where the quasi-particles are in momentum space, we can find the Fermi surface of those 2 bands. That's the first step. We make a high precision map of the Fermi surface of the 2 bands. And then secondly, we know the energy gap at each location on these 2 bands, so we can make a map. So this magnitude here is like the magnitude of the superconducting energy gap at different locations. That's what these 2 images show. Okay, so far so good. Now you have a map of the gap on the 2 bands. Second thing we're able to do is measuring the sign difference between the gaps of a superconductor is hard to do. But these 4 guys, 3 of whom are quite renowned, Hirschfeld, Ehrman, and Mazin, found that interband scattering of potential impurities, simple impurities, has a term in it which has a product of the magnitude, not the magnitude, the signed value of the hole light gap multiplied by the signed value of the electron light gap. That predicts that you should be able to measure scattering interference between these 2 bands and determine from a model whether it changes sign or not. So we were able to implement that. I won't bore you with the results, but we can show very clearly that the 2 bands I just showed you, the 2 gaps I just showed you, have opposite signs. So now this is what we see. Here, there's a gap which is highly anisotropic. It's 15 times bigger here than there. And here, we see another gap which is highly anisotropic, but it's normal in orientation to the first one. So if I plot delta as a function of k, the overall gap structure looks like this. Or if you don't like this bishop's hat picture, the gap on this band as a function of angle looks like this. The gap on this band as a function of angle looks like this. And they're of opposite signs. Great. Now,
does it mean it's extended S?
Say again?
Does it mean that it's extended S? Yeah.
So I dare not answer that question because of things that Una has taught. Yeah, it's a nematic crystal.
S and D are the same.
Fourth approximation is extended S.
So it's a sign changing gap.
Okay.
Yeah.
So if you had a Fermi surface in between, you'd see a node. If you could.
There has to be a line of nodes somewhere in momentum space.
There will be nodes somewhere.
Yeah. Right.
You just don't have a Fermi surface there.
All right. So far, so good. This is just a laborious and rather exotic measurement of the gap structure of a rather different.
Without having the other 2, being able to see the other 2 pockets, you can't really say, how large one component is over the other. S and D should be both there because it's C2 symmetric. So you don't have the
but the technique.
UX of C4.
But the technique that Hirschfeld and Mazin and Ehrman introduced allows you to measure the sign difference between the 2 order parameters, whether it's admixtures of S or D or whatever.
The sign difference would be there,
Sign difference.
irrespective of.
Yeah.
But it's not like a boring S wave, right? An S wave.
No, it's not. It's a sign changing S wave. So let me show you what it is. It's not boring at all. So what we're after is orbital selective superconductivity. So the first thing you can say is, let's take this Fermi surface, and here's the measured gap structure. And now let's go to the literature, specifically this literature, and look at the predicted gap structure for antiferromagnetic spin fluctuations where all the quasi-particles are coherent, which is here. There should be virtually no gap on this low Q band, and there should be a large gap on this band, but it should be orthogonal to the direction in which we detect the large gap. So there's essentially no correspondence between the spin fluctuation theory for the gap structure and what's observed. However, We could consider, yeah.
But these calculations are not assuming that the system is in pneumatic phase.
No, they are, yes, they are. They use a band structure which is already C2 symmetric, and they use RPA for the spin fluctuations. Yeah.
So why is the gap small?
Pardon?
Is that a simple way to understand why the gap is small on the
Yeah.
inner pocket?
Yeah, I had the same question. Why isn't the gap?
So you have to read the linearized gap equation in these papers, and so I don't think I should answer that question, but I think I know the answer. All right. So, okay, look, we have these weird gaps. They change sign. They're on these tiny little pockets, and they're enormously anisotropic, but they have no nodes. It's a weird situation. One thing I noticed, I think my students might give me credit for this, but probably not, is that the orbital selective contribution to the Fermi surface from dyz, it was very like the gap structure. Here you have dyz orbitals. Here you have none. Here you have dyz orbital weight. Here you have none. That's a fact. That's an empirical fact. Okay. However, you can do a different calculation. You can alter the spectral weight of the Green's functions according to their orbital identity, suppress the dz(x) orbital spectral quasi-particle weight, and retain the dzy orbital quasi-particle spectral weight, and solve another linearized gap equation. You can find a nice parameter set which will give a gap structure very quantitatively as observed. Okay. So here we are. We believe this is direct evidence for orbital selective superconductivity in this compound. And it's the dzy orbitals on the iron atom which form the Cooper pairs. dxy and dzx is doing something different. So this will be reported now in Science in a week or two. That's great. There's a lot of skepticism about this because in order to get this correspondence, you have a sequence of arbitrary numbers, right? You adjust the quasi-particle weight for dxy to a tiny value, for dzx to an intermediate value, and for dzy near 1. So the question is, where do these numbers come from? One answer to that would be a DMFT calculation, which people are doing but have not done. But another answer would be to do another experiment where you measure those numbers independently and find out, does it make sense empirically? So here's the other experiment. Visualize the orbital selective Mott structure of the quasiparticles. So how can we do that? Well, we can see the quasiparticles. Now we're in the normal state. We just image the quasiparticles. Here they are, scattering off iron vacancies. And from these movies, you can get a great deal about the momentum space structure of the quasiparticle states in the system. And if I show you the Fourier transform, it's vividly anisotropic. It moves predominantly along this direction. This is the A direction of the orthorhombic crystal. But when it passes the chemical potential, it rotates, and then it moves predominantly along the other direction, which is the B direction. Very strange. It's not a technical mistake. Our very good friend, Tetsuo Hanaguri, had studied the normal state of this compound several years ago, and his data and our data are in very, very good agreement. It isn't a property of the experimentalist or the STM or the tip or the symmetry of the tip or the identity of the impurity or who grew the sample or anything. It's a property of the material. Okay, now let's look at our band structure. A fully coherent band structure. You just set the quasiparticle weight for each Green's function to be 1 for every orbital and calculate what should happen in Friedel, in the normal state. So that's what we have here. Fully coherent 5-band Friedel calculation. You see it's reasonably isotropic, but it's C2 symmetric. It approaches the chemical potential. It passes the chemical potential. It rotates. This is the dxy band out here, and this part rotates and disperses in the opposite direction. That's the prediction. It's completely inconsistent with the data, which disperses only along this direction. There's no dxy band. We don't see it, and neither do photo emission. But it does rotate at the chemical potential. So that's one prediction, fully coherent, no orbital selectivity. Now, we know the values of these numbers. There's actually only one important number. If the z of the xy is suppressed to a very small value, it's approaching localization, then it's just the ratio of the zy and the zx, the ratio of these two numbers, which controls what happens in the quasi-particle interference. So now we do the calculation for this set of quasi-particle weights. It looks like this. It's highly anisotropic along the crystal A axis because we've knocked out the orbitals in the other direction. And then when you come to the chemical potential, it rotates because dzy band is along the B direction above the chemical potential in this band structure model. Okay, so here's the bottom line. Here's the prediction of a fully coherent 3-band model of iron selenide. Here's the prediction for an orbital selective Mott phase. Here's the data. I can run these movies and you can form your own opinion about does this one match this or that in a more appropriate way.
So if you assume the impurity scatter...
Say again?
So the model for the impurities?
It's a delta function in real space, so it's homogeneous in K space. The T matrix doesn't have any weights as a function of location. It's implausible that if it was an internal structure of the scatterer, that it would simultaneously produce this result and an anisotropic gap structure in momentum space for the same parameters. So we don't believe that it's a property of the scatterer. We have a good idea what the scatterer is. It's a vacancy on the iron site, so it isn't a very complicated object. It's just a delta function potential.
And that would scatter between different orbitals.
It will. Yeah, it will. It will. So in our model, it's a diagonal T matrix.
It does not scatter between different orbitals. It's diagonal.
Oh, sorry. In our model, it could. In our model, it's a diagonal T matrix. That's correct. Yeah. Yes, sir. I think this is the second last slide. So save up your cannon shot. And
Shooting private.
no, we have to go to another meeting on the weekend, so we have to survive for a few more days, right? So here's the non-orbital selective QPI. Here's the data. Here's the orbital selective QPI. Here's the non-orbital selective model. Here's the data. Here's the orbital selective model. The difference between these is that dxy, which is this thing, is knocked out of the scattering interference. All of these data are in very good agreement. We believe we're visualizing the orbital selective Mott phase. And we know that this has nothing to do with the tip, because we can do the same experiment over here and over there. We're in two different domains, but it's the same observer. So this has nothing to do with the technique. And finally, the ratio of these two numbers that we need to get the gap structure is within maybe 15% of the ratio of these two numbers that we need to get the normal state electronic structure. So that's our point of defense, that this is the correct argument. So the point of this presentation was to say, here you have a doped Mott insulator producing a high TC superconductor a la Phil Anderson. And here you have a Mott insulator. It's an orbital selective Mott insulator producing a high TC superconductor in the strong correlation limit a la these guys. Okay, thanks very much.
What you are saying that Z factor on different orbital systems.
Yeah.
People who were doing, like Larvin Fat, etc., who were doing calculations of self-energies, were saying, yes, of course, there are K-dependent self-energies,
Yes.
not omega-dependent,
Yes.
that produce different Z factor on different orbitals.
Yes.
In terms of their calculations, it has nothing to do with Mott phase. It's just strongly interacting system which have different Z factors on different orbitals.
I think you're right. The literature in that field uses the phrase orbital selective Mott phase throughout, and maybe that phrase needs to be deleted. That's...
Wow, impressive. 30 seconds.